Discoveries of new research techniques in the field of biochemistry have been increasing more than ever in the past century. Many of these techniques use combinations of foundational methods, especially PCR for amplifying nucleic acid segments, and gel electrophoresis for separating DNA, RNA, and protein molecules. Today, we'll discuss DNase footprinting, a method that uses these two techniques to study specific protein-DNA interactions. We'll use the well-known lac operon as our model to undergo DNase footprinting, but with a twist. We'll go back in time when the mechanism of repression by the LAC-I protein was unknown. So, at this point, all we know is that the LAC-I gene creates a protein that stops the transcription and the translation of the LAC-Z, Y, and A genes. Our goal is to find its underlying mechanism. Our first step is PCR. We will take the lac operon and amplify it through denaturation, primer annealing, and extension to create a pool of lac operon fragments. Next is end filling. We want to label only the send strand of the fragment with radioactive 32P so that after cleavage with DNase, the cutoff fragment is not visualized in electrophoresis. We will use phosphotransferase to label the fragment, but this also tags the 5' end of the antisense strand. We can't control this, but we can use restriction enzymes to digest the one end and cut off the 5' antisense tag. Next, we'll take the fragment, add a binding buffer to promote protein binding, and add the LAC-I protein we are studying. Though we can't see it, we expect that the proteins are now bound to a certain site on the fragment. This is what we want to study, where the LAC-I proteins bind to and what this tells us about its mechanism. We then digest the fragments with DNase, a DNA cleaving enzyme. We put just enough for each segment to be only cut once. Though we can't see it, we expect that each fragment is cut at a random site except for the site the protein is bound to, since the protein is blocking the DNase activity. Afterwards, we take the cleaved fragment and run it in gel along with a fragment ladder, a control of uncut lac operon, and a control of cleaved lac operon without LAC-I. The last two lanes are our fragments and are key to finding the binding site of the LAC-I proteins. In theory, the missing fragments in the gel correspond to the fragment size that was not made due to the protein blocking the DNase from that site. In the cleaved control segments, we see these fragments at around 5,000 base pairs since no proteins protected this site. This information is key. We now know that the missing fragments correspond to the protein binding to the lac operon at a site around 5,000 base pairs. This tells us the location of the site this protein is specific to. 5,000 base pairs from the 3' end of the operon. We have now discovered the binding site for LAC-I. Though a fairly simple example of footprinting, discovering the specificity of a protein from the use of simple, fundamental research techniques holds great power. From this point on, the role of the protein study can be further hypothesized, whether a repressor, inducer, transcription factor, or many others. Ultimately, the importance of DNase footprinting is clear. With a relatively inexpensive and simple methodology that can study the ever-important interactions of DNA and proteins, its uses in the field are truly endless.